Hi there, Math 2403. Welcome back. Video number 2 of Unit 3. Today we'll be talking about the binomial probability distribution, which is a special case of a discrete probability distribution discussed in Video 1. So let's get right to it. So here we have the binomial distribution. This is a distribution that arises pretty frequently. It's a distribution where it's fairly easy to recognize it because, as the name implies, binomial, there are two possible outcomes. So we'll be studying experiments where there are only two possibilities. You win or you lose, you live or you die, it's true or it's false, there's a success or a failure, etc. In order for it to be a binomial distribution, we'll have to repeat an experiment a fixed number of times. We'll do that. We'll call that n. We'll repeat an experiment n times, and we'll just record outcomes. You win, you lose. You win, you lose. Just repeating the experiment over and over again, keeping track of the results. Just for some notation, we'll use the letter S for success and the letter F for failure. Regardless of the context, they don't necessarily mean good or bad. If I'm interested in you, if I'm interested in the probability of a BCIT student failing the course, then a success is a student that failed the course. So don't let that imply necessarily something that's good or bad. It's just what your main interest is at that time. Our trials, as we repeat the experiment, need to be independent of one another. We discussed the difference between dependent and independent trials in previous probability discussions. This just means that each outcome does not depend on what has happened previously. And then we'll use some other notation here. We'll use the letter P for the probability of being successful and the letter Q for the probability of not being successful, which can also be just written as 1 minus P. The classic example is coin flipping, where you repeat the coin flips a certain number of times. So let's say we're interested in the number of heads we get on 10 flips of a coin. This is a binomial experiment in that it meets the 4 criteria that we listed on the previous page, where we have a fixed number of trials. There are 2 possibilities, heads or tails. The coin is memoryless, meaning that it doesn't matter what has happened on previous flips, the probabilities remain the same from trial to trial, and that probability in this case is fixed at 5 or 50%. For it to be a binomial distribution, you don't have to have the 2 outcomes be equal. In my example about a student failing the course, I would hope that not everyone has a 50-50 shot of failing, for example. But this is sort of the classic example that most people get in their head when they're trying to recognize other problems that might be binomials. In order to do the calculations for the probabilities, the notation and the math, it looks a little more intense than maybe some of the things we've seen so far, where we're trying to find the probability of a certain number of successes in a certain number of trials. So what are the chances that I get 5 heads in 10 flips? Or what are the chances that I get 9 heads in 10 flips? And we can get that probability using the formula given here. There's also a nice formula in Excel. It's actually binom.dist. There's a dot in there. So and then the syntax, which we'll go over in a bit. You don't have to memorize this formula. It will be on your formula sheet. And in fact, I don't have it memorized either because it's rather intuitive once you think about how it works. And we'll go through an example and hopefully it will make some sense to you as well. So we have our good old building science technologists who know things about heat pumps. And I've been studying this problem for years, and I know that the chance that any one of the building science students knowing something about heat pumps is 20%. And I'm going to assume that when I do experiments with building science students, that the students are independent from one another, when they may not necessarily be. Think about yourself knowing about heat pumps. Well, if your best friend is in the class with you, you might be talking about heat pumps all the time, and then they're more likely to know something about heat pumps. And then you can see how you're dependent upon one another in a way. But let's assume that I'm picking building science technologists from different years and they don't know each other in order to make this actually a binomial situation. We want to find the probability that in a group of 6, that exactly 2 will know something about heat pumps. So in this case, we're studying a group of 6. And the probability that any one of them knows something about heat pumps is given there to be 20%. And our variable here, let's call it x, is the number of techs who know about heat pumps. In a group of 6. We want the probability of getting exactly 2. Now, we already have the histogram here because when we were discussing this example earlier, I built it based on this data, that there was a 20% chance that someone knew something about heat pumps. So what we're trying to get in this solution is the area of this rectangle. And you can see that it's, between 20 and 30% will be the answer. In order to do the calculation, we're basically going to use the formula that's above, which is on your formula sheet. Now, I think we can kind of reason this out without using the formula. Leave yourself a little space here, and then we'll start figuring this thing out. If there's a 20% chance of being successful, how many successes do I need? Well, I need 2 of them. So there's a 20% times a 20% chance using the multiplication rule. And then if there's a 20% chance that someone knows something about heat pumps, well, then there's a 80% chance that they don't. 1 minus 20, the complement. In a group of 6, I need 2 people to know it, and then I need 4 people not to know it. So it's 20%. Now think of it as 0.2 times 0.2 times 0.8 times 0.8 times 0.8 times 0.8. That's 2 people that know it and 4 people that don't. That is my success. But now I have to think of the different ways that I can rearrange this data. And if I have 6 things in general, there are 6 factorial ways of arranging them. However, that's only true when they're all distinct. And in this case, a 0.2 is the same as a 0.2. So if, for example, if I just swap these two spots around, it's the same result. Or if I swap these two spots around, it's the same result. But if I had the numbers 1, 2, 3, 4, 5, and 6, and I swap these two numbers around, then it's a different list of numbers. So we have to account for that by dividing this by the number of ways you can arrange the knowers. I have 2 people that know it. And then I have 4 people that don't know about heat pumps. And now we've calculated our probability here. We just need to do this calculation. You have a factorial button on your calculator, but if you didn't, you could just list it out. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And then the denominator, you have 2 times 1 times 4 times 3 times 2 times 1. And then this 0.2 squared and 0.8 to the 4th. The nice thing about these factorials is you get a bunch of cancellations. So you can see the numerator is 30 and the denominator is 2, so there are 15. So if you look at this list up here, there are 15 different ways of writing these 0.2s and 0.8s. Doing the calculation there, we get 0.24576. So these aren't too bad to do. I think you'll enjoy these. We'll do part B here. What's the probability then of getting at least 3 successes in a group of 6? Writing that in math notation, we'll say x greater than or equal to 3. That's what at least means. And you know, when we were solving at least problems before, we often turned them around and did the complement. If we were going to do this directly, we would find the probability that x is 3, but it could also be 4. Or you could have 5 successes. Or you could have all 6. So we'd have to do these 4 calculations using the formula above, which isn't, too difficult. Because 3 is in the middle of this list, basically in this part B, what are we trying to get? We're trying to get the sum of these 4 rectangles. So our number is going to be relatively small, maybe only like 10%. So being able to see the graph is kind of nice. We get to estimate what our answer is going to be. It might be easier to do the complement. The opposite of being greater than or equal to 3 is less than 3. And if we're in a discrete situation, being less than 3 means that you're less than or equal to 2. Remember, there's nothing in between. There isn't a 2.5. There isn't a 2.7. So this is a true statement only in the discrete world. And then we could do this calculation. To get all the cases of being less than or equal to 2, we'd calculate 2 successes or 1 success. And don't forget about none. That's a possibility. You could ask 6 people, do you know anything about heat pumps? And they all could say, no. So that's this case here. And now we have to do the formula well, I guess 3 times, which is actually, slightly easier than what we had before, but we had to do all this thinking first. So I don't know if it really helped us, other than the fact that we've already calculated x equals 2. So I think that's where we really gained. This time maybe I'll use the formula. It's n over, let's write it in the same order that I have it written, because I never use the formula myself. It's n minus x factorial, x factorial, p to the x, 1 minus p to the n minus x. And what we'll basically substitute in for these values rather than me just thinking about it. This first value here we already know, 0.24576. And now we just have to do these other two pieces. Now the first piece is when x is equal to 1. So you plug 1 in for x in your formula. And you replace n with whatever n was. And in this case, it's 6. So we'll go 6 factorial over n, which is 6, minus x. In this example, or this problem we're solving, it's 1. And then we have x again, factorial. And then we multiply that by the probability of being successful, 20%. We need 1 success, and only 1 success. And then we have the probability of failing, which is 80%. I guess I should write it out there to match the format. We're following this formula here. We have 1 minus 0.20, and it's raised to the n minus x, which in this case is 6 minus 1, or 5. And now we have this piece here. Now we have to do the other one. Might as well list that next. When x is equal to 0. Do the substitution. So just remember, replace all the x's with zeros. So you have 6 factorial over 6 minus 0 factorial, 0 factorial, 0.2 to the 0, and then 0.8 to the 6th. Remember, I put these square brackets around here just to be careful with this minus sign that's out here. I'm going to have to add all this stuff together and then subtract it from 1. We can do these on our calculator. Let's see if I can do this. Get the right answer. Let's take our initial result, the 0.24576, and then let's add that to 6 second, and then you find your factorial button. Oops, it's 4. And then we divide that by 5 factorial. And 1 factorial. Uh-oh, I'm already in trouble. I didn't hit factorial, I hit percent. Can I go back up and edit that thing? Looks like it. And then I'm going to multiply that by 0.2 raised to the 1. And then multiply that. Then multiply that. I'm just going to simplify this bit here to 0.8 raised to the 5th. And then add the next part. We're doing this, the last piece here. We have 6 factorial over 6 factorial, which is 1. this cancels with this. And don't let that 0 factorial freak you out. The definition of 0 factorial is 1 as well. So we haven't divided by 0. This whole piece here just ends up equaling 1. So that'll save me just in my button pushing here. So I'm just going to say plus 0.2 to the 0 is also 1. So I just have to do 0.8 to the 6th. And now we have to do, that was subtracted from 1. So I'm just going to go minus 1 and, know that it's not negative because I'm lazy. And I think my calculator will switch from fraction to decimal if I hit change here. So our answer is 0.9, I lost it, 0.09888. And don't let the fact that it was negative there freak you out. I intentionally subtracted it in the wrong order just because I'm lazy. So there's your calculation. There's a roughly 10% chance, like we guessed at the beginning, just looking at the graph. To two decimal places, we were pretty good at our guess. Now Excel can do these problems much easier than we can. This was pretty painful. A little painful. I don't mind doing these. In Excel, there's a function, like I mentioned, called binomial dist. So I thought I'd repeat the same question using Excel. Remember the problem, n was equal to 6. The probability of success was 0.20. And then I want to make the graph. I'll show you how I make the graph. All the outcomes are 0, 1, 2. I could keep copying them down, or in one of your labs you learned how to fill them. And then I calculate the probabilities. Remember, we did the probability of 2 successes. Now I want the probability of 0 success, 1 success. I want to see all of them so that I can create this graph. To do that, you use the formula called binomial dist. As I start typing bin, you'll see some options. We want to use binomial.dist. And then you see that it asks for a couple different items. The first one is the number of successes that you want. In this case, I want the probability of no successes. That's what X is. So I'm going to just type cell B6 there. And then the number of trials in this case was 6. Or I could type $C, $2. And then the probability of success is the next thing it wants. So you see how I'm adding commas? So you actually have to put 4 things into this function. The next one is the probability. That's 0.2. Like I could just type it, or I could use $C, $3, so that I reference that 0.2 that I've already typed. And then the last thing is sort of weird. It's asking whether you want it to be cumulative or not. And in this case, I don't want it to be cumulative. So I want to say false, or it's 0 for false and 1 for true. Or you can just select these with your mouse. The reason I don't want it to be cumulative is I only want the probability of this value. I don't want it to sum up all the previous values. So here's the probability of 0 successes in 6 trials. And if I want all the other ones, now I can just copy that down. And I had already built the graph here so that it's plotting this data. And you can see it's the same picture that we had in our lecture notes. So repeating how to do that, in our example, we wanted the probability of exactly 2. So to get that, I could just say equals binom dot dist. And if I just want to type it all, I can say there were 6 trials. Oh, sorry, 2 successes in 6 trials, 20% chance of success, and no, I don't want it to be cumulative. The reason I don't want it to be cumulative is I just want the probability of exactly equaling 2. I just want this rectangle. So that's when I put a 0 on the end. And there's the answer that matches, hopefully, what we did by hand. In the second question, we did, what's the probability of x being greater than or equal to 3? And we actually switched it around. We wrote it as 1 minus the probability of being less than or equal to 2, only because it's discrete. Now to do that calculation, we can just do a formula over here. I'll say 1 minus binom dist again. And this time I want not just 2, I want 2, 1, or 0. And that's what that cumulative business is all about. So I'm going to say I want 2 successes or less out of 6 trials when there's a 20% chance of success. And here's my opportunity to put a 1 or true for cumulative, because I do want it to sum basically 2, 1, and 0 together. And I also will be subtracting it from 1. And you get the answer that we had when we used our calculator. If I maybe bump up the number of decimal places there, you'll see that it matches what our calculator gave. So this is really handy. In fact, I would use Excel to do most of these problems, as it's very convenient and fast. You just have to be very careful about the complement. Your question had the number 3 in it, but we actually used the number 2 in our calculation. 3 or more has a complement of 2 or less, and that's why we add the number 2 in our formula here. So that's how you do this in Excel. Not bad. In fact, I really like it. So now that we've seen how to do this calculation using both by hand and using Excel, there are also tables that can help you solve these sorts of problems if a computer isn't available to us. We'll do this little example here using a binomial table. Here's the example. We know that 70% of all Masons are going to call in sick at least one day in December. Find the probability that at least 7 will call in sick sometime in December, if we're talking about a group of 10. Is it binomial? Sure. There's a fixed number, 10. There are 2 outcomes. They either call in sick or they don't. There's a fixed probability of success, 70% chance of successfully calling in sick. And we'll make an assumption that they're independent of one another, which may not be entirely true, because one of those Masons in the group of 10 might call up his friend and say, hey, let's skip work and go fishing today. Let's call in sick. Well, then they wouldn't be independent anymore. But since we can't estimate the probability of that, we'll just have to assume that there's no one's influencing anyone else. So what's the probability of at least 7? So we want the probability of at least 7 Masons calling in sick. Writing that in more mathematical notation, let X be the number of Masons who call in sick. So we want the probability of X being greater than or equal to 7. Now, as with Excel, cumulative binomial tables work as less than or equal to problems. So we want to convert every question into less than or equal to. In this case, we'll do the complement. The opposite of less than or equal to 7 is less than 7, but you can't have 6.6 people calling in sick, so the next number smaller than 7 is 6. So we would have to calculate the probability of 0, 1, 2, 3, 4, 5, and 6 using our formula, or we could use a table of values. Here's how a cumulative binomial table works. You first search for the sample size that you're dealing with, in our case 10. So there's basically a table for n equals 10, n equals 11, n equals 12. So it becomes, it's a pages and pages of tables if you want to do problems where n equals 27 or n equals 55. Then in the next column, it's your less than or equal to value. In our case, we want the probability of being less than or equal to 6. So we go to that row of our table. And then we're looking for our probability of success. That goes across the top here. In our example, there's a 70% chance that they call in sick. So that's how we zero in on this answer. So pretty nice. In this case, we have to also remember it's 1 minus that. So it's going to be 1 minus 0.3504. There's a 64.96% chance that at least 7 will call in sick at some point in December if you have 10 Masons. In Excel, again, we would use that binom dot dist. And in this case, we just have to remember to use the 1 at the end of it to remind us that it's cumulative. I have that example open here, I think. Example 7. I built the distribution. In our example here, we're trying to do 7 or more. So, see if it will let me write on here. Maybe not. Looks like not. So we want 7, 8, 9, or 10. We're adding these 4 rectangles together. But to do that, we'll do 1 minus 6 or less. So our formula here is 1 minus binom dist, 6 out of 10, 70% chance of success, cumulative. And you get the same answer that we did from the table. Actually, the tables are pretty nice. They're fast. They're almost as fast as typing these functions in. I find that I might be faster with the table than I am with Excel. You're always given the option to do either, provided that it can be done with the table. The table has a drawback in that it only has certain probabilities in it. If there was only a 64% chance that a Mason called in sick, well, we don't have that in our table. We have 60% and we have 70%. So then we would have to resort to either doing it by hand or using Excel. You have a whole list of tables in your formula sheet. And here's what it looks like in kind of small print. You can see n equals 2, n equals 3, n equals 4, 5, 6. This is the table that we just did. And it keeps going. I'm not sure how many pages of this thing I give you in your formula sheet, but I'll try to pick numbers that are in it so that you have the option to use it if you prefer. If you want the probability that exactly 7 people call in sick, Well, you could do it old school. You could use your formula. There were 10 in total, and then 7 of them had to successfully call in sick, and 3 of them didn't. There's a 70% chance they call in sick, and we need 7 of those types. There's a 30% chance they don't call in sick, and you need 3 of those type, and then you calculate that. Alternatively, you could use your table. You could say it's the probability of being less than or equal to 7 minus the probability of being less than or equal to 6. 7 or less minus 6 or less leaves you with exactly 7. And these two values are in our table. Let's go back there and take a peek at 7 or less and 6 or less. So we knew 6 or less was that 3504, and 7 or less is 6172. So this will be 6172 minus 0.3504. And that'll get us our answer. So we have lots of options here on, how we calculate these things. I get 2666. And if we did it if I want the probability that x is equal to 7, I can just do equals binom.dist, and I want 7 successes out of 10 trials, 70% chance of being successful, and now I don't want it to be cumulative, so I put a 0 on the end. And now you match our answer from before. So we can go back and hopefully. Now, with those binomial distributions, the shape of it changes depending on which n you pick and which p you have. If you have a small probability of success, if p equals 0.1, then the smaller categories get filled. If you have p equals 0.9, then you don't have many in the early on stages, and then you have a bunch later on. So the shape of the binomial distribution changes based on what your probability of success is and what n is. But one of the neat things about the binomial distribution is that the mean of it is really easy to calculate. If I tell you there's a 10% chance of being successful, and you repeat an experiment 10 times, how often do you expect to be successful? Roughly 1 out of the 10, 10% of 10 things. If I tell you there's a 90% chance of being successful and you repeat something 10 times, you'd expect to be successful 9 times. And that's what the average ends up being. It's just n times p, which is much simpler than the calculation we had to do expected value for just a general, any old probability distribution that's discrete. The standard deviation is also very simplified. It's just the square root of np and q. Remember, q is 1 minus p. So we can measure the variability of these sorts of plots as well. So once we know that, we can then again apply the empirical rule or Chebyshev's theorem. A lot of times they're skewed, you can see. So we would be using Chebyshev's criteria in that case. But sometimes these things are actually fairly symmetric, and then we can use the empirical rule. In fact, it turns out that binomial distributions tend to look like bell curves as long as you meet 2 criteria. And that's np greater than or equal to 5 and nq greater than or equal to 5. If both of those statements are true, you tend to get bell curves when you plot your binomial distributions. And that allows you to use the empirical rule. I did one example here where I just wrote down n is 20 and p is 25%. And then I used, binom dist here in Excel. And I put in x, and then 20 was my n, 0.25 was my probability of success, and I put 0 in for cumulative for the last parameter because I wanted each one of these bars. I just copied that formula down. And as you can see, you get a pretty decent looking bell curve. And this one does meet the criteria. If I take n times p, that's 20 times 0.25, which is equal to 5. And n times q is 20 times 75%, which will be 15. Both of these numbers here are greater than or equal to 5. So we've satisfied this criteria. You just have to know that about the binomial distribution. If these two conditions are true, pretty decent bell curve. I may have been a little dishonest here in my plot in that I only plotted up to 12 to make it look more like a bell curve. It is a bit skewed to the right, but I don't feel too guilty about my bad graph because you'll notice that what I left off of it was essentially 0 to 4 decimal places, or at least to 3 decimal places. So I'm now just asking you to, trust me about this criteria. We can now apply this to a little example. Last one of this unit, actually. And at least it's a new example. We're going to study solar panels. Some company says, who installs these things, says 10% of them need fixing in the first year. And they didn't like that. 10% was a high repair rate. So they modified them. They modified the design of these and then installed them for a year, and then they did another test. So they studied 200 of the modified ones, and then we'll ask some questions. So assuming that the modification has no effect at all, what would the mean and standard deviation be for this group of 200? So we're studying 200 solar panels, and we're saying the probability of them successfully being defective is 10%. So the opposite of that is 90%. 10% of them have potential problems, and 90% then are good. Is this a binomial situation? I think so. They're either good or they're bad. We have a fixed probability. We'll assume they're independent of one another, and we have a fixed number of trials. We're doing the experiment a bunch of times now, 200. Because we know it's binomial, that allows us to calculate the mean using the binomial formula, which is just NP. So 200 solar panels are studied. There's a 10% chance of them being defective. So on average, we expect 20 defects in a group of 200. The standard deviation is an easy calculation. It's the square root of NP and Q. So we'll do 200 times 0.1 times 0.9, and then take the square root to get the average distance from that mean, which is 4.24 defects. So we're wondering at this point, did the modifications help? Like, before we did modifications, 10% of these things had problems. Then we did modifications, and we studied the results of 200 modified solar panels, and we found that 14 of them actually needed fixing out of the 200. So does this give us enough evidence for us to conclude that the modifications were actually helpful? Like, can we conclude that 14 is a big enough improvement over what used to happen? And what used to happen was we'd have 20 defects, typically, in a group of 200. Well, 14 is better than 20. So hooray, maybe things have improved. But is it enough better for me to conclude, absolutely, I know the modifications were worth the expense, and this is definitely going to save us money going forward? And I'm not so sure. Is 14 far enough away from 20 in order for me to make that sort of decision? Now, since we have a bell-shaped distribution here, and we can see that I plotted it for you, and this is a pretty nice bell. We can check it using our criteria. You know, is NP greater than or equal to 5? Well, yeah, it's 20. Is NQ greater than or equal to 5? Sure, it's 180. It's 200 times 90%. That's also greater than or equal to 5. So this tells us that we have a bell shape. And since we have the bell shape, we can apply the empirical rule. And the empirical rule said that 95% of z-scores are within 2 standard deviations of the mean, or 95% of all scores are within 2 standard deviations of mean, meaning the z-score between -2 and +2 is, very typical or usual. So is 14 an unusual result? That's what we're getting at here. If we calculate the z-score for the 14, we had our mean of 20 and our standard deviation of 4.24. I get a negative z-score, you can see, negative 1.41, which isn't that unusual. It's low. It's below the mean, but it's not way below the mean. Not that unusual. So with that information, can I conclude that the modifications helped? And I think the answer is, I don't know. Because I didn't get an unusual result. Had I gotten a number here like -3 or -4, then I would say, yes, something really weird happened. After I modified things, I got a result that is way different from what I would expect had I not modified things. So in this case, because I ended up with a value between -2 and 2, I really can't tell. I'm happy that I ended up with a negative number, but I think I would need to continue studying this problem in order to make a strong conclusion about whether or not the modifications really helped. So I'm not going to send out the bonus checks uh, to everyone involved in modifying the solar panels because I don't quite have enough information to make a decision of whether or not it helped. Because had I not modified at all, I could have studied 200 of these and seen a result of like 14, and it wouldn't have been surprising at all. So this is an introduction to decision making and some of the stuff that we're going to be doing going forward. We're basically combining probability together with some data in order to make a decision. I think that's it for this unit. I will see you all in the next one. Take care.